Hello, everyone, and thank you all for joining us. The views, opinions, and technical analysis presented during this webinar are those of X-Rite and not necessarily those of UL. The appearance of this content on UL sites does not constitute an endorsement by UL or its affiliates. Today's webinar is How to Meet Quality and Sustainability Goals with Digital Color Management Tools and is presented by X-Rite. Your presenter today is Felix Schmollgruber, Sales Director EMEA in CP&M. My name is Abby Pura with UL, and I'll be moderating today's event. Please send us your questions by typing them in the question tab located on your screen. We will also have poll questions today, so please answer them when they come up on your screen. We are recording today's event and will send you a link by email when it has been posted to ulprospector.com. Now, I'd like to turn the presentation over to Felix. Would you like to begin?
Thank you, Abby, for the introduction, and welcome everyone to this webinar. So what we will be covering today is a journey from design through visualization to specification, formulation, the production and the quality control of colored material. And that can be anything, of course, anything where color is relevant now, or let me call it slightly different. Let me just see, here is my controls. So a quick introduction on who X-Rite Pantone is. We are, our mission is kind of to advance the creation, communication, and delivery of color and appearance. And we do this in various market segments. So that's a beauty of ours, that we really work across multiple market segments. And the fascination for me for almost 20 years or over 20 years with this business is that we are quantifying scientifically a human sense, which is considered one of the most important human senses, color, or color perception and color vision. So basically, CP&M stands for Consumer Products and Materials. So I'm in the field of mostly automotive, textiles, plastics, coatings, or cosmetics. So anything which is a consumer product or a material. The other business unit we are running is print and packaging, where print, packaging, and photography, design, and pre-press also for the printing is considered. Now, we want to kick off with a first poll question here in order to understand whether you are familiar already with color measurement or color management altogether. And this will be, do you currently use color measurement instrumentation already? And we provide you 4 options. Yes, an X-Rite device. Yes, a different industry device. Yes, I'm not sure about the make, or no. I would be very glad if you could answer that, because that helps me leveling in on what the audience is like. Abby, you will let me know by when we have some results, right?
Yes, we have quite a few results at this time. It looks like yes, an X-Rite device is our current winner.
Mm-hmm. Okay, very good. All right, thanks for that. So we do have quite some experienced people here. That's appreciated. Now, how to meet the quality or sustainability goals with digital color management tools. That's the title. For me, it's kind of starting with design. It's kind of the story of Lisa and Mike, I call these two. So I wanted to go a little bit by a story because I think it illustrates what we're dealing with here in the markets and market segments we serve. So basically, Lisa is a designer and has to create new colors almost daily. She's, of course, collecting all kinds of inspirational items for her color choices. Mostly she shares them with her suppliers, like Mike, who is the supplier here, to get a prototype sample of the material she needs in that color. So here you see she's choosing a color, she's sending a sample to Mike. Now, unfortunately, she doesn't know how to specify the color for material in a way that she finally gets what she wants. And quite often she gets this glove to the left and not what she's willing to get, which was the glove to the right. So you see there is a difference. And both actually, Mike and Lisa, don't know how to deal with that. So what has happened here? Lisa provided a painted sample to Mike, who made a manual match of that fleece fabric. She looked at her reference under fluorescent light source, and he had an incandescent light source. And these are two substantially different light sources. So what they have is Lisa and Mike had a mismatching lighting condition, and they had materials and colorants of different make or different type. So that's where the trouble starts. And we call this effect metamerism. I don't know if you heard this before. So metamerism is an effect that some colors might match under one light condition, but they might mismatch under a different light condition because they are made from different colorants or pigments. Let me show you what that looks like. On the top right here, you see two spectral curves. That's actually the fingerprint of color, which we measure with our color measurement devices with our spectrophotometers. And you see here that, of course, these two curves are mismatching quite desperate or quite substantially. And now if we watch these curves under daylight, and you see here the little rainbow colors is actually trying to mimic the spectral distribution of daylight. So all of us know that light consists of all colors of the rainbow, ranging from blue through green, through yellow, orange, and red, short wave to long wave, and daylight typically looks like that. So we have lots of light energy across all the wavelength with a little bit of a dominance of the blue. And you see, if we have light across the whole spectrum here, then these differences between the curves, which under and overcuts each other multiple times, they eliminate. And apparently such two samples, even though these curves are totally different, look the same under daylight. So why do they look different under different light? If we watch these or observe these two samples under a fluorescent light, for example, and fluorescent lights are typically having peaks of light energy. In this instance, we have a fluorescent light source with 3 peaks, one blue, one green, one yellow, as you can see. And apparently these 3 peaks are exactly at the point where there is a large difference between the two curves. And that is highlighting that difference, of course, to the human eye. And therefore, these two samples look totally different or show a difference on that particular light source. So that's metamerism. Now, what should they do? We believe they should go digital, right? If Lisa starts off in trying to convert her inspirational items, whether these are physical samples of some sort or pictures or whatever, into a digital color reference like Pantone colors, then of course there is already a high potential, or there's not only a high potential, there's a safety that Pantone colors are all available in spectral data, so in real fingerprint, physically correct color data. And that Pantone reference, she could actually tell Mike, and Mike could use a computer-aided color formulation software like our Color Eye Match software to load the reference data, the reference spectral curves from the Pantone Live Cloud and actually perform a match with a computer-aided color formulation system, which is free of metamerism and which actually is also faster than if he would try to manually visually match a sample which he receives. Now, what is color formulation? The benefits are quite obvious, and the return on investment is really pretty fast in many cases. I put up a little comparison here between a manual color formulation and a computer-aided color formulation. Typically, customers tell us that if they don't have the software, they need 10 to 15 steps to match difficult colors, where with the computer and the spectrophotometer, where you can measure the sample, as you can see on the image below here, and then you basically measure the sample, you click the button, and you get a recipe instantaneously or within seconds. It might need 1 or 2 corrections based on the other process parameters, which might be variable, but you basically reduce your number of trials to a minimum, and we talk about a factor of 5 almost, right, on what we are faster. There is no extra steps to match transparency in case you have plastics, like we see here on the picture, because we can capture the opacity or the hiding power or the volumetric behavior of plastics with the instrument. I'll be talking about this later again. And this makes the next one actually makes the return on investment. You can always be rest assured that you get your pigment or your colorant loading 100% correct. Whereas with manual color matching, most people use way too much colorant, and the colorant is typically the expensive raw material. So this is actually a critical point of saving money if you produce colored material, because if you need less colorant, then of course you save a lot of money. Reproduction speed, if you need to create a new batch with varying batch lots, or if the customer reorders in a year from now and you have different colorant or raw material batches, then of course you're also faster because you have the legacy data. You can start off from the recipe you did a year ago and just correct it one time to match the current conditions. So your overall time to color match is much faster, and your rejection risk, so basically the risk of disappointing Lisa, is of course very low if you use the computer and the software. Besides that, how does it work? Just a quick introduction. So you basically measure your sample, or you pull the data from the cloud, as I just said. Then you define your properties, your resin or material type, your opacity and thickness requirement, a target delta E. Delta E stands for color difference. That's the metric we use for color difference. And your sorting criteria, since this is called a combinatorial formulation, and you will get a multitude of formulas on display from which you can choose. Then you formulate the color with the click of a button. Then you review the results. Then you produce a sample of your chosen recipe. You verify that sample by measuring it with the spectro against the digital reference. And if you're happy with the results, you report the recipe and hand it to production, or you produce the final batch. And that's, of course, a very slick and slim process. If you're unhappy with the result, which can happen if you have a batch-to-batch variation of pigments or colorants, then, of course, you can go in iterations and correct. And then you can do as many corrections as you want in order to get back to a matching result. And that is, as I just said, much faster than doing it by hand. Besides that, of course, Lisa and Mike should have and go for defined lighting conditions for the physical samples they still need to evaluate. So those materials which are finally going into production, they should, of course, get a consensus and an agreement on at which light they would look at those. And you see here, they both use now a Spectralite QC light box, which offers a multitude of different light sources, a daylight simulation, cool white fluorescent, which is commercial fluorescent light used mostly in North America. TL84 is another such choice for the European markets. Ultralume is also widely in North America. And you see even incandescent and horizon choices, or ultraviolet light we have to assess optical brightness. So a neutral, controlled environment for physical samples is an essential, of course. So moving digital, Lisa, of course, now today even wants to go one step further and work with digital materials, not only digital color. So what does that mean? The question really is, could Lisa get a digital twin of that fleece material she's aiming for, which actually looks like the real material on screen in a rendering application she might use, right? So the comparison between what's a flat, solid color versus what is really an appearance. Now, let me quickly introduce you to what appearance is, because that leads us in the second category here into visualization. Appearance is not just color, it's not just a picture. It is kind of the visual sensation through which an object is perceived to have attributes such as color, texture, gloss, transparency, translucency, and even more. And this is a technology or a vision we have as X-Rite for quite a while already, that we developed something which is called the Total Appearance Capture System. So what is material appearance? Appearance is actually a sum of a multitude of things. It's not only the material consisting of the properties I just mentioned, gloss, texture, transparency, translucency. It's also the geometry of the object. So this flower pot here has a specific geometry. It is, so the size and shape of that, it is the scene, what's the surrounding in which I would want to look at this material, virtual and real surrounding. It is perceptual transformations, contrast sensitivity, tone mapping, adaptation and context. And it is the viewer, what's the distance and the angle to the object from which a viewer or an observer looks at the object. What we are trying to do with total appearance capture is to actually create the digital material, and we put that into what we call the appearance exchange format, AXF. Now Lisa can do, of course, get this, right? With an AXF file, she can combine color with 3D texture, with surface gloss, with pattern, with and actually create designs in rendering applications which are matching the physical truth of a material. So that is basically going beyond color. As you can see here on this blob, this virtual object, we have two different textures, but the same color. And Lisa can now make assessments on what these different materials in terms of texture would look if they are colored the same way. She could also do this like for effect pigments. So here we have two painted panels in a virtual light booth. So these are not photographs, but really digital renderings. And the question here is, are these two gray or silver? Now, of course, they are silver. As you can see, if we change our viewing angle to these samples, then of course they show their behavior. And here we actually talk about effect pigmented surfaces or gonio appearance. So angular dependent appearance of materials, which we also can track with total appearance texture capture technology. And we started this off like 5-6 years ago with a material scanner, which you see on the top of the screen here, our total appearance capture scanner, TAC7, which was a kind of a very complex device in the size of a washing machine to really make a full hemispherical assessment of what happens to any ray of light positioned onto a central sample when it is actually reflected back from that sample. That was kind of an effort to do a so-called virtual ray tracing, and then a modeling to actually compress a massive amount of raw data into something which we call the AXF file. Today, we are trying to scale up this technology using the same software platform called Pantora, and we have since 2021 the Pantora Connect module to it, which connects to our legacy or standard devices like benchtop sphere spectrophotometers or multi-angle handheld spectrophotometers, or our very unique hyperspectral imaging spectro, the MetaView, in order to be faster. If you consider the average time the TAC scanner takes for scanning a material, which is about 10 minutes in average, these devices can actually capture materials within seconds mostly. And then you can mix and match things, right? You can load color from color libraries. You can load color from CXF files, which is the predecessor of the AXF file, the so-called color exchange format. And you can combine them with other attributes from an AXF file like texture to totally new materials, which will be physically correct. And then you can submit them to quality control or color formulation as we have just seen it earlier. So here you see that as an example, we can take a ladder texture measurement from a MetaView, combine it with Pantone Fandex spot color measurements, also done with the MetaView or based on the MetaView. We took them from the digital library. And then we can combine these two properties, texture and color, to totally new materials with a certain confidence that we will be able to produce these materials physically correct, because both these channels, the texture and the color information, has been deriving from a real material. So we can actually mix and match and design new stuff here nicely. This is also possible with metallized objects. So here you have a metal texture measurement done from a MetaView and a metal spot color measurement with a CI 7800 sphere spectrophotometer. And you can combine that into a new brushed metal texture type material. Or You can actually, with a CI 7800 benchtop spectrophotometer, you can measure volumetric materials like a step chip, a plastic chip, a transparent plastic chip, and then combine this with a grain measurement or a texture measurement to a new textured transparent material. And of course, you can then use these materials to render them over any given object. Now, this rendering piece, of course, is relevant or is depending from rendering programs and rendering engines to understand AXF. And here you see the ecosystem we're having, which is actually supporting AXF. So this is, of course, a journey. There is more and more programs to be accepting AXF. So we consider this like the PDF of material of the future. And the market is really appreciating it, that we do all this, because everyone today goes into virtual prototyping, into virtual metaverses, even into, so everyone goes digital basically with their material lifecycle management, and AXF is a fundamental element to support this in terms of appearance. Here you see some other inspirations from different materials to different paint materials. This one on the top here, top left, even having a color flop, as you can see, it has a kind of a shimmer from green to red. So that's actually captured. Here you have a silk, which also has an anisotropy, so it changes its look and appearance under different viewing angles. Or this houndstooth here, of course, has a 3D texture to it. And here you see transparent materials, a high transparent plastic chip and a semi-transparent or translucent plastic chip. So all of that can be physically correct, captured as a digital twin of this material. Now, the next element and challenge Lisa and Mike, of course, have is the specification of material or color. And here we have the next poll question, of course, which is, how do you currently specify color if you are a specifier, so designer, research and development, marketing, or receive color specification if you are in material management or development and manufacturing and sourcing? Is it a verbal description? Is it a physical sample? Is it a color reference code like a Pantone code or a Mansell color or a RAL NCS color? Is it LAB data? Is it spectral data, or you have no clue, don't you? You don't know. So I'm curious to see your answers on that question here.
We'll let a few more votes come in, but it looks like so far LAB data is the most common way they use to currently specify color.
All right, that's an interesting answer, coming with a certain challenge, which I'm happy to address now in the next couple of slides. So Lisa and Mike got the challenge to share their final proposal of a new material prototype with the sourcing teams for them to get serial production going. Without a digital workflow, they have to duplicate physical samples to have enough master samples to share with suppliers. So thankfully, we are kind of over that, because you in the audience say you get LAB data today. But the challenge, if you do have physical samples floating around and a multitude of duplicates, is called the error stack. And the error stack is a challenge because we start from a master physical standard. This is the prototype which Lisa and Mike finally tuned to their desire and agreed upon as the master reference, right? Now, LAB, which hopefully most of you are familiar with, is a three-dimensional system. So colorimetry is three-dimensional. We have a lightness axis from black to white, and we have A and B from green to red and B from blue to yellow, and any color or any set of LAB values represents a specific spot in this virtual color space here. So the problem is, if we go by physical samples and we actually need to duplicate our master standard in order to have enough transfer standards or shipped physical standards to our suppliers. So we ship a physical standard to a supplier which differs from the master standard by a delta E2000 of 0.2. That's the color distance. And to give you an idea, everything exceeding a 1 is a visible difference. Then our supplier actually produces an approved match from the received transfer standard, which is again differing by 0.6 delta E. And then they take this sometimes in production after they have Lisa's approval. And there is again variation in the production. And in this instance, apparently, unfortunately, everything was shifting towards the lighter. So we basically have a total difference to the master standard by 1.3. Now, supplier B is running through the same exercise, and apparently or coincidentally, they shifted to the darker. So they actually are away from the master physical standard by 1.2. And the total difference between the two products we get delivered is actually 2.5. And then we're back to our two gloves, which are mismatching, and nobody knows why. Because everyone thought they actually keep tight tolerances, but we had a stacking up of the errors, right? If we go digital, then we wouldn't ship any physical standards, but we would actually do measurements with a controlled fleet of instruments, and we would refer everything back to this one unique digital master standard, which is kind of a set of LAB values. The challenge with LAB values versus spectral data is that LAB values are typically only valid for one illuminant observer condition. So if we talk about LAB values, or if we talk about color in general, we have three things which are all three variables somehow. We have light, we have the object reflecting or transmitting the light, and we have someone observing the object. And the observers are variable and the light sources are variable, as we have seen earlier in the metamerism example. So we need to fix these two in order to do the math to derive to a set of LAB data or values. And the LAB values come with the challenge that they're only valid for one such light observer or illuminant observer condition, like we call it. And therefore, spectral data is the better choice unless we are precisely taking care about using the same observer and illuminant conditions when we talk about LAB values. But LAB values is already better than physical standards, that's for sure. So that much to the poll question. Anyway, so you see our total variation is now reduced to under 1, and we get actually the expected results from both suppliers, which is good. Finally, we have designed, visualized, specified, and formulated color. And now, of course, we talk production and quality control. And that's basically an overview only to give you an idea that, of course, X-Rite does have a solution there, right? So we have really, from handheld to non-contact devices, we have a range of instruments and software products in all measurement geometries. There are 3 measurement geometries which we do color measurement with, from very reliable handheld devices to benchtop precision spectros, which you see here in the middle, to actually hyperspectral imaging devices like our MetaView, which is combining a spectral engine with a camera. So you can really also measure spot colors on a pattern, or you can pick multiple colors from a pattern and process them precisely with spectral data. And we have also non-contact inline solutions for web production, like you see here, a coil coating production line where we can actually measure across the web and control the color in the process flow. Now, the big question remaining is, if we have all this from design to quality control, how do we fit it all together and what's really necessary? And that leads to a question about digital color communication. We are true believers of digital color communication, but we believe it needs an ecosystem of connected data sources, instruments, metadata, and an audit trail for being able to remove a multitude of physical samples moving around, and from being also able to know what the condition and the specification of the digital data is which we share. And if we don't know the instrument condition, which for the instrument which was used to measure the digital reference, we cannot trust it. If we don't know whether the sample was positioned properly to the aperture of that instrument, it's difficult to trust the measurement. if we don't know the metadata along the material type and the specification and who the measurement personnel was and where it was measured geographically, at which site and which factory, etc., we miss information. The audit trail is a digital signature that no one can tamper with our data, because if I have a text string of measurement values, I could, of course, manipulate them. We avoid or we eliminate that by doing an audit trail in our IQC iMatch software. And of course, if we go to cloud computing, then of course we also can use the Pantone Live Cloud for Pantone digital color to go from there and actually centralize everyone to one Pantone reference, since X-Rite and Pantone are a joint company. Now, pros and cons for digital versus physical samples are quite obvious, right? Digital samples don't change, alter, degrade, contaminate. They are available from a centralized source. They can be shared instantly over the internet. Of course, that's maybe the disadvantage. They require a fleet of accurate, stable, and controlled instruments. If I cannot make sure that one instrument is measuring exactly the same like the other, I have a hard time to compare readings from two instruments against the same digital standard. For physical standards, the pros are a little less and the cons are much more. Of course, physical standards represent the current status quo, but unfortunately they age and they can contaminate and they can scratch and whatnot. They are independent of instrument-to-instrument correlation. So what's actually the single one con of digital samples is here a real pro, but of course the rest is all negative here. So how do we actually make sure we have a controlled fleet, an accurate fleet of instruments of different make and model in different locations across the globe? Our answer to this is called Net Profiler. Of course, every instrument manufacturer for color measurement devices, or any instrument manufacturer in general, has typically performance criteria for the instrumentation. And the two most important ones are inter-instrument agreement. So is my instrument measuring the same like yours? And repeatability of the single instrument. And that also makes the price difference for many instruments depending on what type of accuracy you want to have. That's like the performance criteria, like horsepower and consumption for a car, if you wish. Now, you see here three different types of instruments, and they typically operate in a specific inter-instrument agreement, which is the size of the bubble. But they also operate in a specific centroid, or because of their physical make and physical nature. And what Net Profiler does is it profiles all these instruments to one central point. And what that provides you is it gives you the factory specification in the field. And I want to explore this a little bit. So if I have an instrument in my laboratory, let's say in the USA, and I have 72 degrees Fahrenheit, 22 degrees Celsius, and I have a 50% relative humidity, and I read a reference, and I chose a simple reference, which is a mid-grade, the center of the LAB point. So we have an L value 0 to 100 at 50, and we have A and B values at 0, because this is where the gray shades are. And that's the theoretical reference of that neutral gray, like we call it. And now we fly over this reference to a production site, let's say in Taiwan. And there we have 31 degrees Celsius or 88 degrees Fahrenheit and a much higher relative humidity. So it does something to the instrument and maybe even to the sample. And apparently that sample now reads a different set of LAB values. So we do have an instrument-to-instrument difference, which is already quite substantial from 0.4, 0.4, and 0.3 here. Now, if we net profile our instruments, and I'm explaining you how that works, we log on to the Net Profiler server. That's why it's called Net Profiler. It's a server. We get a set of ceramic tiles, and those tiles are also the tiles which the manufacturing uses or our service teams uses if they recertify and calibrate instruments. We measure those tiles. I put a little temperature gauge here because these are temperature depending, so we need to input the temperature here as well. Then we compare the readings which we currently took on our instrument in the current condition the instrument's operated in, and compare them to the reference readings or to the digital reference values which are on the server for these serialized tiles. And that allows us to create a profile. And that profile can be downloaded to the instrument. And then we do a verification reading of the tiles to see whether the user was actually reading the tiles consistently. So we compare these readings to the first taken readings, but we also apply the profile now to compare these readings to whether the profile actually has a positive impact and improves the accuracy and tightens the instrument to the centroid. And if that's the fact, we receive a certificate. And that data is also going back onto the server, so we can do some fleet management if we are working in a network of multiple instruments and review all these instruments and performances on the NetProfiler server, or in the future on our tool called X-Rite Link. So fleet management is a big topic for large customers of ours. Now, coming back to our scenario where I had the instrument in the USA and the instrument in Taiwan, and we had those differences. If I do the same readings now with a net profiled instrument, I'm getting closer to the truth on both sides, and therefore I get a better instrument-to-instrument correlation and agreement, and that is the enabler for digital color management and for being able to eliminate the shipping of samples, but go against the 5000 digital reference with both these instruments in both these locations. Now, with that, I'm already at the end of my presentation. I'd like to thank you for your kind attention, and we have one last poll question for you, and we open it up for questions and answers.
Hello, everyone. Please make sure you answer the poll, and then we will move into Q&A. Please remember to put your questions in the question tab located on the right-hand side of your screen. We'll try to get through as many as we can. So our first question, how difficult is it to create the calibration set for a color formulation system of paints?
It depends on what the material is. If paints basically are typically liquid, so it's very easy. You can actually tint the systematic amounts of base material and then pigments, right? A 99 base material to 1% pigment mix is something you would mix up. You would apply a drawdown to a contrast card, and then you would dry it, and you could measure it, because you basically need to create systematic mixes of your colorants with your base materials in order to teach the software the optical properties of your colorants so that color formulation works. For paints, it's rather simple. For plastics, it's a little more complicated, because you might need to do you might need to mold plastic chips, and you might need to pelletize, run plastic raw material and colorants through an extrusion line first. But for paint, it's rather simple.
Okay, great. Thank you so much. Our next question, what about LABCH data? Is that more specific and clear than only having LAB data?
Thank you for the question. It's actually the same thing. LAB data is actually going by Cartesian coordinates, A and B axis, and then the L axis as the third dimension through it. With C and H, you describe actually the same color spot with an angle and the distance from 0. So H is the hue angle, starting at A plus 0 degrees, 90 degrees, 180 degrees, 270, 360. And the distance from 0 is called the chroma. So the same spot in color space, I hope you can see my video where I'm trying to use my fingers to explain this. So L, C, and H is the same like LAB. It's just comparing polar coordinates against Cartesian coordinates. In some instances, C and H is actually better to use, because if you actually apply delta LAB or delta LCH tolerances, that makes a big difference. Because LAB tolerances would be squares in that color space, whereas LCH tolerances would be trapezoids in that color space aligned to the hue angle, and these are in better correlation to the visual perception. So if you can use LCH, you're a little better off than with LAB. That's the short answer in a nutshell.
Okay, great. Thank you so much. Our next question. How is the error using DE instead of DE 00 during quality control activity with a spectrophotometer on metal painted surfaces, for instance?
Huge. The flaw of the LAB system, which was invented by a gentleman called Richard Hunter, and then was further developed by the CIE, the International Commission for Lighting, Commission Internationale l'Éclairage. It's an association with a French name sitting in Vienna, Austria. The downside of the LAB system is that it is not fully linear to the visual perception of humans, because it was actually originally developed or started very early in the last century. Like the first developments have been done in 1931. And the delta E formulas, the color difference formulas, have been actually put through advanced math. And the latest one is actually the delta E 2000, and the delta, or 00, and the delta E 2000 is at about 98 to 99% of visual correlation to human observers, whereas the standard delta E from 1976 is at about only 85%. So if you can use delta E 2000, you're better off across the wide color ranges. Only, I mean, you say metal paints, right? If it's neutral achromatic metals like aluminums or really like looking like blank metal, so like gray shades basically, then you might be better off with a standard delta E, because in the neutral range, the standard delta E is a little more sensitive and therefore more precise to the human perception as well. But overall, across the entire color range, you're better off with the delta E 2000. We have quite some questions. That's good.
Yes. Our next question. Hi, I'm really interested in the perceptual lightness or darkness of a color, for example, a stair stripe. Both L and CIEY values are expressed on a scale of 0 to 100, yes? So why do L and CIEY values differ for the same color?
That's a difficult one. I'm not sure, quite honestly, whether the Y value ranges from 0 to 100. Now you struck me with a real deep detail. I'm not sure that is the case. I can confirm that the Y value expresses the lightness as well. So that's really now an advanced question. LAB values or LABCH values are derived from X, Y, Z values, which are called the so-called tri-stimulus values, which are derived by multiplying the spectral curve we measure with the light source we have, and then with the three human observer functions, small caps X, Y, Z, and that will give capital X, Y, Z, and Y is actually standing for lightness. But I'm not quite sure whether 100 is the same like an L value of 100. I'm happy if I get the email address of this person who asked that question to investigate and come up with a specific answer, but I don't have the full answer to that myself now, I must admit.
Yes, we are recording all of the questions. This is for everyone. We're recording all of the questions today and all of your email address for those asking questions. So if we need to expand on any of these answers or if we don't get to them, please know that we will respond to your questions. Yeah. Our next question.
If I may pick one myself, Abby, there was one question: is NetProfiler designed only for X-Rite spectral devices, or reduce the difference for spectrals between different producers? We basically focus on our own devices, and if it's about onboard profiling, we can only do that for our own devices. So we can actually put a profile on the instrument and then also operate it with different software. We do have one competitor, the second largest one in our market, which is a company called Datacolor, and we can profile Datacolor instruments too. So we can actually also profile a mixed fleet of instruments, but that's the only competitor we're doing that for, because they are very strong or widely accepted by global supply chains, especially in the textile and the paint arena. And we have customers who use our software and a mixed fleet of Datacolor and X-Rite instruments, which can be harmonized with NetProfiler.
Okay, great.
All of our devices measure optical density too. That was another question. Do any of the new devices measure optical density? I don't know, Abby, do you have one on scope which you would want me to answer?
No, you can take whatever you'd like. But I have one ready if you'd like one. What is delta E is acceptable based on your experience?
Yeah, as I said during the presentation, and it's basically if you use a perceptually corrected delta E formula, which is basically either delta E CMC, which was the first such formula, or delta E 94 or delta E 2000, I would go for a 1 as a limit, right? Across all colors. If you use delta E 76, which is the original delta E, which is just the geometrical delta E, you need to be careful. I would go for anything which has a chroma below 10 or A and B values below 10. I would go for a 0.5, and then anything which is going higher, yeah, to a 1. But for example, if you have two bright yellow shades, so you have a B value of like 80 units, which is absolutely feasible. Let me bring back the LAB graph on screen quickly. Here, so if you are in the far out yellow, you could have a delta E76 of 3 units, which is non-visible to the human eye. Whereas if you have 3 units delta E in the center and in the neutral shades, in the gray shades, you have a huge difference. And that is simply caused by the fact that the human eye, the retina has actually two receptors, the rods and the cones. And these cones are doing the color vision and the rods doing contrast vision, which is why our human eye is such a nice high dynamic range kind of camera, if you wish. So we can actually cope with very little amounts of light and with very high amounts of lights. But as we all experience at night, we don't see colors because at a certain point the cones are actually turning off, and then the color vision is off, and we only have contrast vision. And to give you an idea, that contrast vision with the rods is actually 100,000 rods come to 1 cone. So that's the ratio. And therefore, we are way more sensitive on gray shades or on lightness difference than we are on color difference. And that's why this LAB system is not uniform to the human perception. So delta E 2000, a limit of 1 is actually appropriate. If you consider the 3-dimensionality, right? If you define your standard here and someone delivers within the range of 1 to the top and another one delivers within the range of 1 to the bottom, you might actually have to cope with actually having a variation of total close to 2 units. And that's, of course, again, then exceeding the limits. So that's why some customers go more aggressive, which in turn, if someone reduces from a delta E of 1 limit to a 0.5, that makes your instrument fleet accuracy or your inter-instrument agreement even more important again. I hope that answers the question.
Okay. Our next question, how accurate are handheld and tabletop machines? And with that, what temperature is best to measure color during mass production using a tabletop machine?
Always standard temperature range is like 72 Fahrenheit or 22 degrees Celsius, and a mid-range relative humidity is always the best condition. I'm trying to answer a second question here, which was when you have to profile the spectra, do you have to set it up on the same temperature as the reference instrument? Ideally, yes, but Net Profiler does have a temperature compensation. I hope I did mention that during the presentation. So we enter the current temperature and we ship those Net Profiler tiles, the ceramic tiles, with a temperature, with an electronic temperature gauge to know the temperature of the environment, because it also affects the tiles. The spectro, a benchtop spectro, or especially our benchtop spectros, they have 3 thermometers built in, and they have a thermal compensation method built in. So they actually track the ambient temperature which we have during a measurement, and they also compensate slightly for it. Of course, the ideal case is always that you have equal temperatures. I would personally say the benchtop instrument is less sensitive on temperature variation than the handheld instrument is. But in both cases, if you net profile them at the given surrounding condition, you're better off than not net profiling them. Of course, some materials can also be changing their colors depending on temperature. That's called thermochromacy. And that can be quite substantial, like it is with those ceramic tiles. Some of these ceramic tiles change their color by 1 unit per 2 degrees Celsius difference. And therefore, we actually have to do a compensation. The reason why we use ceramic tiles for net profiling is that these are long-term stable, but they are, of course, slightly thermochromatic, and therefore we need to compensate for thermochromacy, which is easy because it's a linear effect. So if I know the color at 2 temperature points, I can actually build a function to compensate for the temperature. I hope this answers the question.
Okay, our next question. When doing a formulation with plastics using your software, as a base, you need to input the software with the LAB values in each component. After a few iterations, can you put in the values into the software so it improves the following suggested mixes?
Yes, absolutely. It's not quite the LAB values. The LAB values are calculation from the spectral values. So we do measure systematic mixes, as I mentioned. And from those systematic mixes, of course, we have so-called calibration sets or colorant files. So we have collections of colorants, which we then use to do the combinatorial math formulation. With every formulation we save into the database, we get a reference point, which we can use for a new formulation later on. So the system is kind of machine learning. And with every correction we do, we also have that learning. And on top of that, our QC part, quality control section of the software, which in our case is always combined in one package, which is not the case with some competitors. We always have quality control functions and formulation functions in one software, or in the same software platform. Of course, you can choose to only go for quality control. But with the matching software always comes quality control, and that's important because you might have batch-to-batch variation of your colorants, which you get delivered from your supplier. And what you can test with the quality control function of the software is, as a means of incoming inspection, is the colorant strength, which is relevant for pigments, right? You might have a batch of pigments which is stronger in its color than a next batch of pigments, and you can adjust your calibration set or your colorant file you use for color formulation for the actual batch colorant strength in order to consider it. Let's assume your colorant strength of the original batch you have used to calibrate your colorants is set at 100% level. The next batch you receive is only 98% level, which means you would systematically need to use more in every formulation where this colorant is used in order to get to the same colorant strength. And that's actually something the software considers. So the system is learning as you go, which is really good and which customers like a lot. I hope that answers the question.
I think it does. Our next question, is it possible to measure and classify the pattern and the color of marble laminated material? We had already used a semi-variogram without big success.
Can you tell me who asked this, that I can read it out? I'm not sure I fully understood it.
Yes, this was asked by Stefano Petisi. Is it possible to measure and classify the pattern and the color of a marble laminated material? They had already
marble laminated. So I think that question relates more to the total appearance capture system. Marble as a natural material, same as wood grain, is basically possible to be captured, but it's mostly not tileable, right? So if you actually, the minimum sample size we need for a total appearance capture scan is 7 by 7 centimeters, or about 3 by 3 inches, if you wish. Marble is normally not for marble or wood grain or certain natural materials. This might be too small of an area to really eliminate the tiling, right? If I would always have the same types of patterns to repeat on a virtual digital object, then if that is the question, right? Basically, you can scan marble and we can capture it, but it's not tileable, unfortunately, to be mapped over a larger object in the end. I hope this answers the question.
Yes, our next question. What spectral ranges are typically measured, 380 to 370, and how are the calculations processed? 10 nanometer intervals or 5 nanometer intervals? I've seen many instruments still using 10 nanometer spacing, which I find odd given the capacities of new instruments.
In our case, our instruments, most of our current instruments measure from 360 to 750. The CI 7800 and 7860 measure up to 780, and they measure in 10 nanometer intervals. Or they compute or they output the data in 10 nanometer intervals. Internally, they measure even in higher resolution. Our inline spectrophotometers measure a true physical 1 nanometer resolution. You finding odd that we don't compute 5 nanometer intervals is actually, it's a philosophical question in a sense, because the higher resolution you would compute or process. So most instruments, even those who are actually already outputting 5 nanometer intervals, they don't have an internal physical resolution of 5 nanometers, because the challenge is you have to actually implement a slit to split the light to a very tiny fraction in order to map the diffraction into the rainbow colors precisely onto the sensor without overlap. And that actually cuts off a lot of light. And if you the least light you have, the more noise you have, the less accuracy you have. And having a 5 nanometer resolution, in my personal opinion, is mostly relevant for yellow shades or for step curves in the spectrum, where you really have the necessary mapping. I would still say that 10 nanometer resolution is widely sufficient for the most applications we are dealing with today.
Okay, well, that was our last question for today. Thank you again for attending our event today. Just as a reminder, we will send responses to any questions we weren't able to get to today. And we will also send you an email with the recording of this event so you can watch it at any time or share with others of your company. Thank you again for attending, and have a great rest of your day.
Thank you for the good questions and for your attendance.